Welcome to Unite Now, where we bring unity to you, wherever you are.
Hello, everyone. Welcome to Unite Now, and in particular to this presentation about Unity tips for optimal performance. I really hope that you enjoy the talk, that you learn something useful, and that you have fun. My name is Arturo. I'm a games evangelist at Unity Technologies. Please feel free to reach out to me on Twitter. That's my Twitter handle on there. Share your optimization tips, share your thoughts, and please provide feedback. If you want us to continue working on similar content, also please let us know. So this is the agenda for today. We're splitting the session in two parts. So this is what we will be covering today. And if you want to watch the second session, please be aware that it's going to be released in any upcoming week. And before jumping into the presentation, I want to make a quick note about optimization. Optimization is a very important topic for real-time applications such as games, because unlike other types of media, we need to make sure that things execute in a given amount of time with certain resources, which in most cases are very, very limited. Also, remember that optimization doesn't mean the same thing for different projects. For example, in some games, in some projects, if you change something to the C# code, it might not make any difference. But if you adjust something on the light baking, it's going to make a huge difference, and vice versa as well. I guess I can summarize optimization in two words. One being a budget, and the other one being profiling. Budget, meaning the resources and constraints such as memory, resolution, time, even money. And profiling, meaning the process of measuring the usage of that budget, knowing and understanding how far we from using all these resources that we have. And for measuring, the best idea is to use the right tools. Unity provides some built-in tools to help you profile, and the recommendation that I can give you here is to always profile on the target device. If your target device is a mobile phone, then profile on the mobile phone. You can profile on Unity, but the results will be different from actually testing on the mobile device. Let's start talking about some of these profiling tools. First, we have the Unity Editor Profiler. And the Unity Editor Profiler is a tool that you can use to get performance information about your application. You can connect it to devices on your network or devices connected to your machine to test how your application runs on your intended release platform. You can also run it in the editor to get an overview of resource allocation, and this while you are developing your application. We also have the Memory Profiler. This is a separate package that you can add to your project. This package adds an additional Memory Profiler window to the Unity editor, which you can then use to analyze memory usage in your application in even more detail. You can store and compare different snapshots in time to find memory leaks more easily, or to see the memory layout to find some issues with fragmentation, which we'll be covering soon. But I just want to make sure that you know these tools. Then we have the frame debugger. The frame debugger lets you freeze playback for a running game on a particular frame, and then view the individual draw calls and steps used to render that frame in particular. The debugger also lets you step through draw calls one by one, so you can see in great detail how the scene is constructed from its graphical elements. Now, we talked about tools that are developed internally by Unity and are provided inside the editor or even as a package. But there are other tools that other vendors develop that can help you in different scenarios. So here the recommendation is to take a look at these different tools. And this is just a simple list, but think about what you want to profile and then look for a tool that helps you with that task in particular. So for instance, Xcode instruments allows you to, comes with various instruments to profile like memory. It works particularly well for like iOS devices. Visual Studio and its debugger works for different devices, but it even allows you to attach to an Android device. If you want to know more about like the graphic side, RenderDoc is a tool that you can use. We also provide a Unity build report tool to understand, once you build your game executable, which assets are taking which space in the final build. So those are other tools. Now, to understand many problems, we have to understand, at least at a very basic level, concepts such as the memory, the processor, the GPU, and how they work. In this section, we will take a very simplified look at two places in runtime memory. One is the stack, one is the heap. Is a space in memory that stores variables that are created inside functions, as well as the parameters received and the function itself. This structure stacks all the values as they are executed, which allows us to call functions inside other functions. In this example, you can see how we first put the update and the spaceship health values. So as we start executing our update, we reach the update and we stack or we push the function itself and the variable that we define there. Then as we continue through the execution of our update, then we call the heal function, and you can see how then we push the heal function and the two parameters that we're sending. Then we keep executing, and then we jump from heal to the second line, which is going to call the damage function. So we pop the heal again. So we are popping that value in the stack. And when we execute the damage, we simply push that back. After the damage function returns, we pop that function, and then the update finishes its execution, and we pop that again. We don't have the risk of issues such as fragmentation here or garbage collection here, but you need to be careful about one thing, which is the stack overflow, meaning that you run the risk of calling too many functions, that the stack simply keeps pushing and pushing and pushing data there until there's no more space in memory, and then you overflow the stack. You run into that problem. The heap is another region in our memory. This is larger than the stack. And here's where we put all of our classes instance objects. Usually, every time that we create a new object, we will get the next available spot in the heap. Once we destroy the object, we don't necessarily release the memory right away. We just mark it as unused, so the garbage collector can free that memory later. Here, what we have to understand is that the process of instantiating and destroying objects is generally slow. So we want to avoid basically what is called allocating memory in the heap as much as possible. Another thing to consider here is that if at any point we need more memory than the memory that we have, the heap will grow its size. It's going to grow twice its size, and it's not going to shrink back ever again. So you run into that problem. And also, those empty spaces that we leave might yield to fragmentation. So let's take a look at the example that we have here. Similar to the previous one, here on the update, we will instantiate a new spaceship, and you can see how we reserve the memory there. And then we instantiate the values there in the heap. So we have our spaceship with two vector trees and two float values. Then we instantiate a bullet, the same. We allocate the memory, and we have a vector tree and a float value there. Then we instantiate another bullet, and you can see that, again, we have a vector tree and a float. Then we will destroy the first bullet that we created. But this destroy, remember, doesn't actually freeze up the memory space. It's just going to be marked as, okay, I'm not using it, but the memory is still going to be there. The space is not going to be available to be used by another object right away. And then we go to the next destroy, and you can see here that is the same, that we are not freeing up that space. That process of freeing up that memory comes from the garbage collector, which we will see how it works in a quick second. But just remember that this is an oversimplification. Now, with the previous knowledge, let's talk about the garbage collector. And remember, this is an oversimplified view. Take your time, do some extra research on the topic, or let me know if you would like to have an in-depth presentation on any of these topics so we can work on that. Now, back to the heap. In Unity, we don't necessarily worry about requesting memory space and freeing that space. That's great for convenience, as we simply can instantiate and destroy the game objects and move on. But as we mentioned earlier, this comes with some issues. Here, we will take a look at the garbage collector, which is this mechanism that cleans up the memory that we previously allocated. In this example, you can see that even when we are calling destroy, so remember the new spaceship, the new bullet, and then we start calling destroy on the spaceship, even when it's marked as not used anymore, we still have the memory over there. After we end up executing our update for this frame, then, and this is just an example, the garbage collector might be executed. And what it has to do is to iterate through the collection of objects or memory in the heap and find the stuff that needs to be released. So you can see the garbage collector says this bullet is still in use, so I'm not going to do anything. This other bullet is now ready to be released, and the same for the spaceship. But again, just remember, we want to avoid those spikes, because imagine we are running our game and then the garbage collector has to release memory of hundreds of even tens of game objects. This is going to cause a spike in your profiling or in the execution of your game. Okay, now let's jump into the actual meat of our presentation, and we will start by talking about some general tips. So when we're programming games, we end up needing more than just one instance of our game object, right? And what we do is we use data structures to have collections of our data or our objects. If we're using a data structure that is not optimized for a specific use case, we might end up incurring in performance problems. For example, if you're searching or iterating or on a collection, or in using more memory than the one that you probably need. One example is that indexing in an array or a list is cheap, but adding and removing objects or new elements is more expensive than doing it in a dictionary. So you have to understand the data structures to make sure that you're using the right one for the specific use case. So here the tip is that you analyze what problem you're trying to solve, evaluate the different data structures, and choose the one that fits better in most of your cases. Okay, this is a very common one about object pooling. So creating and destroying objects is a very common task when we are programming a game, and we usually do this using the instantiate and the destroy functions on the game object class. If we are doing this very frequently, the garbage collector will be having more work to do every time it collects. Given the big amount of destroyed objects that we will have at multiple points, this will cause a spike in CPU time, as well as the risk of having heap fragmentation. We already know the problem about those things in the heap. The recommendation is to implement an object pool. There are a lot of implementations online. You can come up with your own implementation. The principle is always the same. It's you instantiate some objects before you actually use them, and instead of destroying those objects and then creating new ones, what you do is you recycle them. So you hide them somewhere, you restore their original values, and then you just simply put them in the desired position once you would like to instantiate a new one. The problem here, or the thing that you have to be careful about, is to decide the size of your pool and the initial size or the initial number of objects that you want to have in your pool. Because If you need more objects than the objects that you have in your pool, then you will basically have to grow the pool size, and you will run into similar issues to the ones that you were trying to solve. Perfect. So now on scriptable objects. If your project has a prefab that stores unchanging data in an attached monobehavior script, meaning as in our script on the right, we have this monobehavior called enemy, and we have a max speed and a radius attack. And imagine I have multiple enemies with this monobehavior attached, and the properties, the max speed and the radius attack, are going to be the same ones for every game object. So I'm using this for configuration. Every time I instantiate that prefab, it will get its own copy of the data for its components. So even if the data is the same for all of them, we're basically keeping two floats on top of the rest of the monobehaviors that we have, two floats per enemy, when the value we know is not going to change and it's going to be the same for each one of them. Now here the tip is to use a scriptable object instance that is referenced in your prefab. If you do that, you will just use the memory for one copy of the data. So on your right side, we have this enemy configuration class that extends scriptable object, and you can see that we have the same max speed, the same radius attack, and now in my enemy class, I simply have a reference to that scriptable object. And every enemy can have the same reference to that enemy configuration object or scriptable object, and even if we have thousands of those enemies, we will just save using the memory for these two flows, which is pretty convenient. And there are other uses for scriptable objects, but this is just one tip around them. It's a common practice for coding safety to generate properties with getters and setters in our code. A property is basically a method call which incurs in time spent in the stack frame to add up in situations where multiple calls are found. This might not be an issue in many cases, but in tight loops, it might be a potential optimization candidate. So here the recommendation is to use what we call a define symbol or a preprocessing directive. So you can see here in my code on the right, I'm saying, okay, if I'm running a development build because I'm still developing, or if I'm running on the editor, then have everything as a property, right? But else, meaning this is running on the device, this is a published build, just use it as a regular variable. And you can define your custom scripting define symbols in the player settings, under project settings, that you can see here, that you can say, okay, this is a development build, or this is a test build, or whatever you want. And then Unity, if that flag or that symbol is found, is going to take that route in the code and not the other one. Now onto the resources folder. And when accessing assets from code, it's a common use to use the resources folder and the resources.load or resources.unload assets. There are a couple of gotchas with this approach. One being the fact that any asset included in the resources folder will be bundled with your game. Even if we don't use it, everything that is in the resources folder is going to end up in the final build. But another problem is the fact that the number of assets in the resources folder, used or not, directly affects the startup time of the game. And this is because the header of the file, because also you have to know that the resources folder becomes like a large file. But this header will contain a lookup table for each of the assets that are included. And this lookup table is loaded in memory once the game starts. So that's something that will slow down the start of your game. The recommendation here, and I hope this is a tip that you think it's worth it, is to simply avoid using the resources folder and to start using the addressable asset system to manage the loading and unloading of your assets in a more robust and efficient way. The package is free. You can just get it from the package manager, the addressable assets package. Okay, another, I will say, pretty common tip, but still worth talking about it. And here, the thing is, when you're creating new mono behavior scripts, Unity by default will create them with an empty start and update functions. Also, when you're coding, sometimes we implement other Unity messages just for testing purposes, and those end up not being used in the game, but we just leave them there, right? We think like, oh, they are not being executed, doesn't matter. But having empty Unity functions, even when they are empty, will incur in a small performance overhead. While for just one game object, this might not be an issue, it's easy to adopt those empty functions in hundreds of game objects and then getting performance issues. The recommendation is to remove any empty Unity function, such as start, update, wake, etc. And if you still need them for developing or for debugging purposes, you may want to again use some sort of additional compilation. So for instance, here, if I'm running on the editor, I want to have the update with, of course, with something inside it. But if this is not running in the editor and this is a build executable, then simply this won't won't make it into the final build. Now, the next tip is about having heavy initialization logic in your awake and start functions. This is particularly important for when your game launches. A bit of context, Unity renders the first frame right after the awake and start functions are executed, which in some cases, this might lead to a splash screen or loading screen that takes longer to be rendered because, you have to wait for every game object to complete its start and awake functions. Imagine that you want to show your main menu and in the background, you have some 3D objects doing some idle animations, some AI to navigate. And if you put all that initialization logic in there, the user will see the first frame rendered even after everything else is initialized. This might be more visible on mobile platforms and might even produce a store rejection for taking too long to show the first image. So the recommendation is, when possible, just try to remove heavy logic from the start and awake functions and activate or instantiate objects right after the first frame is rendered. In the previous example, what you could do is just show something and then start or initialize those objects. So the next one, if we're using the Unity animator and we're assigning parameters from code, or when we are assigning properties to materials or shaders, we tend to use the methods that take the string as a parameter for the property name. I think this is usually just because it's more convenient and it's the method that we remember. But internally, Unity doesn't use those string values at all. What Unity does is it hashes them into the integer property value. If you're calling these multiple times, what Unity is doing is computing that hash multiple times. And we'll call the integer overload of the methods anyway. So, and if you're doing this in an update or in a very tight loop, this might become an issue. So the recommendation here is that since this ID value of the property is deterministic each time you run your game, meaning that it's not changing, we recommend you to hash the value at the beginning and then use the version of the method that receives the property as an integer. So you can see here that instead of doing something like animator.setTrigger and then jump, we, on the start, generate the ID using, for instance, animator.string to hash. And then we use that ID to say animator.setTrigger and send the integer. Again, this might look like a very particular optimization, but when you're doing this many times, you basically are saving time and processing time, which becomes important. Now, one on the side of the hierarchy, and for multiple reasons in our hierarchy, we might have a very nested structure. In some cases, this is for logical reasons. For example, to apply transformations to some of the children of an object, etc. When we transform a root game object, there's this event called onTransformChanged. This message is propagated to all the child of the the root game object that we are calling that transformation on. Even if those don't have any renderer, meaning that we won't see any visual change, we are incurring in unnecessary transform computations for translation, rotation, scale. And additionally, deeper hierarchies will make the garbage collector to spend more time traversing the hierarchy. So the recommendation here is that when possible, avoid having very deep hierarchies when it makes sense to have one. And when it makes sense to have one, optimize it by separating the game objects that actually need a transformation propagation from the ones that don't. And remember, this also helps with better garbage collection types. So you can see here on your right side of the screen, we have this root game object, and we have another children, which is the game object A, and that game object A has a game object V. In this case, imagine we want to rotate or translate our game object A. So what's going to happen is all the objects in that like sub-hierarchy are going to be transformed, even if they don't need to. In this case, imagine game object V doesn't have any renderers, so we don't need to transform those. The recommendation here, using the tip that I just gave you, is to flatten the hierarchy and have the game object V to be a direct child of root game object. In this case, now game object A, if that object rotates or translates or whatever, is not going to affect game object B and all its children. So this will be more optimal. And remember, for just one object or a simple hierarchy with one root game object, this might not be extremely important one, but when you have more and more, and I think there are many cases when you end up having like hundreds of objects, these can make a big difference. So you know that the accelerometer frequency defines the frequency at which Unity pulls the accelerometer information from the device. In a game that doesn't require the accelerometer, having it enabled or set to a higher than needed rate might impact performance. So the recommendation here is to make sure to disable the accelerometer frequency if your game doesn't use it, or if it does use it, adjust it to the minimum possible value. So just bear in mind that the higher the frequency, the smoother the reads will be, but you will be basically having some impact on the performance because you're pulling the hardware. So by doing this, you can save some CPU processing time in mobile platforms, of course. There are multiple ways of moving our game objects in Unity, and depending on the use case, we tend to use transform.translate. And if we want the object to also collide with others, what we do is we add a rigid body and a collider. When moving an object with a rigid body attached, but via its transform, this triggers a physics world recalculation, which can be expensive in complex scenes. So here, the tip is, if you want to transform an object that has a rigid body component, use the rigid body classes methods. For instance, rigid body dot move position instead of transform.translate. Also make sure to do these on the fixed update instead of the regular update. So basically, if you're using transform translate, use the update. If you're on fixed update, if you want to use a rigid body move position or add force or any of those, do that in the fixed update. When we are instantiating objects at runtime, it's a common use case to add components to define the object's behavior. Something like, as you can see here, I have a barrel game object and I instantiate it, and then I want to add some components. So I do the add component, and then I have my game object behaving the way I want. Calling add component at runtime is very inefficient, especially when we are doing multiple of these calls during a frame. When we add these components or mono behaviors at runtime, what Unity does is, first, it checks if the component has the disallow multiple component attribute added. If the attribute is found, then it has to check if there's another component of the same type added. So meaning, let's say character data, that script doesn't allow you to have multiple components on the same game object, then Unity first checks if there's that component, so it has to traverse all the components that the object already has. And then Unity also needs to check to see if the required component attribute is set. If it's set, meaning that this component requires other components to be added, then it has to add the other components and do the same checking as we did before. Finally, there's also the cost of invoking the awake function on all the recently added mono behaviors. All these previous steps incur in heap allocations. And we now know that we don't want to do that because that might have an impact in performance and garbage collection times. So we want to avoid that. The tip here is to try to avoid adding components when possible at runtime, especially on critical parts of your code. You can, for example, use prefabs when you need to have like these components added to a specific type of object. Okay, and yeah, also remember that in some cases, maybe in your particular case, this doesn't make any difference. So remember to profile and see if this actually saves some. Cool. It's common to have the need to find a game object in the scene, probably because it was created at runtime or during its initialization. And the same is true for the need to find a component in a game object, either within the same game object or in another game object. We know, and probably you've heard this tip millions of times already, but that GameObject.find and all the related functions require Unity to iterate on every game object and component in memory, meaning that this will be particularly slow in complex scenes. GetComponent queries every component attached to a game object, also incurring in a runtime cost. And the more components call getComponent, the more the cost adds up. And this is particularly more expensive if you are using getComponent in children, as the query grows in complexity. The recommendation here is to cache the reference to the object that you just found. Basically means do the find once and then use the result. And you particularly want to do this in your start function or your away. On your start function. So you find that game object and then you use that cached version throughout your game. If that reference might change, find a way to not having to do the game object.find every frame or multiple times every frame. Perfect. So that was it for the first part of our presentation. Before you go, remember to follow the UniTips hashtag every Tuesday on Twitter. Share your tips. And if you just want to learn tips, go there. Also, I recommend you to watch this Unite Now presentation on profiling. This is a session by my colleague Chiro. If you are interested in the diagrams that I just showed you, go and get them on my GitHub. And remember to tune in for the second part of the presentation coming soon to Unite Now. And feel free to reach out to me on Twitter. That's my handle. Let me know if you would like us to work on similar content or to dig in more in particular topics that you will be interested in. But I hope you had fun. I hope you learned something. And thank you so much for watching.